Welcome to Chapter 11, where we dive into the world of simple linear regression and correlation. This is one of the most powerful and commonly used statistical tools in engineering and science. In this chapter, we'll learn how to model and analyze the relationship between two variables, make predictions, and quantify the uncertainty inherent in real-world data. We'll start with the fundamentals and build up to hypothesis testing, ANOVA, and correlation. Let's begin by understanding what regression analysis is all about. Regression is a statistical method used to model the relationship between a dependent variable, also called the response, and one or more independent variables, or predictors. Why do we use regression? There are three main goals. First, prediction, estimating the value of the response for given predictor values. Second, explanation, understanding how changes in the predictors affect the response. And third, control, identifying which predictors are most influential so we can manage a process. A critical point to remember is that the relationship is not exact. Real-world data always includes random variation, from unmeasured factors, measurement error, and natural randomness. Regression helps us model the average relationship while quantifying that uncertainty. In engineering and science, we constantly want to predict or explain one variable using another. For example, we might want to predict the tar content in a chemical outlet stream based on the inlet temperature, or predict a car's gas mileage based on its engine volume, or estimate a house's price based on its square footage. The key idea here is that the relationship is not exact. Even if the inlet temperature is the same, tar content will vary slightly from sample to sample. That variation comes from unmeasured factors and natural randomness. Regression allows us to model the average trend and quantify how much individual points deviate from that trend. Now let's define the problem more formally. We want to model the relationship between two variables. The independent variable, denoted as *x*, is the predictor or regressor, the variable we manipulate or use for prediction. The dependent variable, denoted as y, is the response, the outcome we want to predict. When we have only one independent variable, we call it simple linear regression, or SLR. When we have two or more predictors, it's multiple linear regression, or MLR, which we'll cover later. Think of a real engineering problem, predicting fuel efficiency of a car based on its engine size. In SLR, we fit a straight line through a scatter plot of our data to best capture the linear trend. Now let's define the problem more formally. We want to model the relationship between two variables. The independent variable, denoted as *x*, is the predictor or regressor, the variable we manipulate or use for prediction. The dependent variable, denoted as y, is the response, the outcome we want to predict. When we have only one independent variable, we call it simple linear regression, or SLR. When we have two or more predictors, it's multiple linear regression, or MLR, which we'll cover later. Think of a real engineering problem, predicting fuel efficiency of a car based on its engine size. In SLR, we fit a straight line through a scatter plot of our data to best capture the linear trend. Let's write the theoretical SLR model. Y equals beta plus beta x plus epsilon. The deterministic part, beta plus beta x, represents the mean or expected value of y for a given x. The term epsilon is the random error or disturbance, the noise, around the line. It's important to understand that this is a conceptual model. There is a true line in the population, but we can never observe it directly. We can only estimate it from sample data. The error term epsilon lumps together all sources of unexplained variation, omitted variables, measurement errors, and randomness. We typically assume that epsilon has a mean of 0 and constant variance. Use simple linear regression. When you have only one relevant predictor, the relationship is roughly linear, and you need a simple, easy-to-explain model. Multiple linear regression models, the relationship between two or more predictors, and one response using a linear equation. The equation is y_i equals beta_0, plus beta_1x_1i plus beta_2x_2i, up to beta_kx_key, plus error. Each beta_j is a partial regression coefficient. It's the expected change in y for a one-unit change in x_j, holding all other predictors constant. For example, predicting house price from square footage, bedrooms, age, and location index. Use multiple linear regression when several factors influence the response, which is most real-world problems. Also, when you need to control for confounding variables, or when you want to assess each predictor's unique contribution. The error term epsilon has key assumptions. 0 mean, the true regression line passes through the means of y at each x. Constant variance, the spread around the line is the same for all x. Independence, errors are not related to each other. And normality, epsilon follows a normal distribution, with mean 0 and constant variance. Because of epsilon, y is a random variable even when x is fixed. The mean of y given x is beta underscore 0 plus beta underscore 1x. This is the true regression line. Beta underscore 1 is the change in the mean of y for a 1 unit increase in x. Beta underscore 0 is the mean of y when x equals 0, but that may not be meaningful if 0 is outside the data range. Here we see a scatter plot with a regression line. The dashed line represents the true population line, which is unknown and theoretical. The solid line is the estimated line we compute from our sample data. This visual makes the distinction clear. The estimated line is our best guess of the true line, but due to sampling variability, it will never be exactly the same. In practice, beta underscore 0 and beta underscore 1 are unknown. We use sample data to compute estimates b underscore 0 and b underscore 1. The fitted regression line is y hat equals b underscore 0 plus b underscore 1x. Y hat is the predicted or fitted value. The fitted line is our best guess of the true line. With more data, the fitted line gets closer to the true line. Let's look at a real example. This comes from a study on water pollution in the tanning industry. Tannery wastes are chemically complex, with high chemical oxygen demand and other pollutants. The researchers collected 33 samples of chemically treated waste. They recorded x equals % reduction in total solids, and y equals % reduction in chemical oxygen demand. We want to see if reducing solids predicts a reduction in oxygen demand. This dataset will be used throughout the chapter to illustrate concepts. This figure again illustrates the difference between the estimated line we compute from data and the true line that exists in theory. The dashed line is the true line, but in practice we never know it. It's a conceptual aid to remind us that our estimates are just that, estimates, not the exact truth. Common uses of SL or in technical fields include calibrating instruments, for example, using a known standard to predict a measurement, and predicting a hard-to-measure output from an easy-to-measure input. In each case, SL or helps quantify how a single input affects an output, enabling prediction and optimization. For instance, we might use temperature to predict pressure, or voltage to predict current. The key idea is that SL is valuable when direct measurement of the response is expensive, time-consuming, or difficult. Now we move from theory to computation. How do we actually find the best line through our data? The answer is the method of least squares. We want to choose the line that minimizes the sum of the squared vertical distances from each data point to the line. Those vertical distances are called residuals, the differences between the observed y and the predicted y from our line. After we fit the line, some points will be above the line, positive residuals, some below, negative. A key property is that the sum of residuals is always 0 for a least squares line. Residuals are incredibly useful for checking model assumptions later. The residual for the ith observation is e underscore I equals y underscore I minus y hat underscore I, where y hat underscore I is the fitted value. Residuals are the vertical distance between observed data and the fitted line. They are the empirical counterpart of the true errors epsilon underscore I. Why do we square the residuals? Squaring ensures that all errors contribute positively, so positive and negative errors don't cancel out. It also makes the problem mathematically differentiable, allowing us to find the minimum using calculus. Minimizing the sum of squared errors, or SSE, is equivalent to maximizing the likelihood if the errors are normally distributed. This method dates back to mathematicians Legendre and Gauss in the early 19th century. Here are the formulas that result from the least squares minimization. The estimated slope is b equals psi sxx, where sxx is the sum of squared deviations of x from its mean, and psi is the sum of cross products of deviations. The estimated intercept is b equals bx. These formulas are computationally stable. Notice an important property: the fitted line always passes through the point x, the means of x and y. Let's apply these formulas to the pollution data. Using the 33 samples, we compute sxx, psi, then b, and b. The result is a fitted equation that we can use to predict the % reduction in chemical oxygen demand from the % reduction in total solids. We now move from simply computing estimates to understanding their statistical properties. We'll see why least squares estimators are good. They are unbiased, meaning on average they hit the true population values, and we can quantify their precision using standard errors. We'll also learn how to partition the total variation in y into explained and unexplained components. which leads to an estimate of the error variance sigma. This is where regression becomes more than just curve fitting, it becomes statistical inference. Unbiasedness means that if we were to take many samples and compute the slope each time, the average of those sample slopes would equal the true population slope beta. This is a fundamental desirable property. The proof uses the linearity of expectation and properties of sums of deviations. Unbiasedness of the intercept follows directly from unbiasedness of the slope, and the fact that the fitted line always passes through x. This holds regardless of the distribution of errors, as long as the errors have mean 0. The intercept estimate b_0 equals y bar minus b_1 times x bar. The claim is that its expected value is the true intercept beta_0. Proof: expected value of b_0 equals expected value of y bar minus x bar times expected value of b_1. Since expected y bar is beta_0 plus beta_1 x bar and expected b_1 is beta_1, the terms cancel, leaving beta_0. So b_0 is unbiased. The variance of the slope decreases as spread in x increases. This makes intuitive sense. More spread in the predictor gives a more precise estimate of the slope. Also, larger error variance carry 2 increases uncertainty. The variance of b_0 is sigma squared times 1 over n plus x bar squared over s_xx. The covariance between b_0 and b_1 is negative sigma squared times x bar over s_xx. These come from b_0 equals y bar minus b_1 times x bar. Y bar and b_1 are uncorrelated, and under normality they are independent, but the covariance formula holds generally.
These quantities are central to regression computations. S_xx measures spread in x, S_y measures spread in y, and S_z measures their joint variability. Many textbooks use this notation because it simplifies formulas. SSE equals sum of squared residuals. Substitute y_i minus y hat_i as y_i minus y minus b times x_i minus x. Expanding the square gives s_i minus to be s_i plus b squared s_xx, where s_i is total in y, s_i is joint variability, and s_xx is spread in x. Substitute b equals s_i over s_xx into the SSE expansion. Simplify, the first term becomes s_i minus 2 times s_i squared over s_xx plus s_i squared over s_xx. Combine the last two terms to get minus s_i over s_xx. So SSE equals s_i minus s_i squared over s_xx. That's equivalent to s_i minus b times s_i. This is the computational formula for SSE. Theorem 11.1 states that an unbiased estimate of the error variance sigma squared is given by s squared. This equals SSE divided by n minus 2, also written as s_i minus bs_i over n minus 2. This quantity is called the mean squared error, or MSE. We divide by n minus 2, because two beta_0 and beta_1 are estimated from the data, consuming 2 degrees of freedom. Why is s squared called a mean squared error? The true error variance sigma squared measures how far y falls from its true conditional mean, beta_0 plus beta_1x. We estimate that conditional mean using the fitted values y hat_i. So the squared residuals, the vertical distances from data points to our fitted line, are the real-world versions of the true squared errors. This table shows the pattern. In a one-sample problem with no regression, we estimate just one parameter, the mean, and the sum of squared deviations has n-1 degrees of freedom. In simple linear regression, we estimate 2 parameters, intercept and slope, so the residual sum of squares has -2 degrees of freedom. Each estimated parameter costs 1 degree of freedom. Degrees of freedom means the number of independent pieces of information left to estimate error variance after accounting for the parameters we've already estimated from the data. Now we come to a very practical measure of how well our regression line fits the data. The coefficient of determination, denoted as R. R tells us the proportion of the total variation in the response variable y, that is explained by its linear relationship with the predictor x. It is calculated as R equals SSR, SST equals 1, SST. SSR is the explained sum of squares, SST is the total sum of squares. R always falls between 0 and 1, and R of 0.85 means that 85% of the variability in y is accounted for by x. and the remaining 15% is unexplained error. In simple linear regression, R is also equal to the sample correlation coefficient R. So if R equals 0.9, then R equals 0.81. A high R indicates a strong linear relationship, but be careful, a high R does not prove causation, and it can be artificially inflated by adding more predictors, which we'll see in multiple regression. Correlation coefficient. The sample correlation coefficient R equals S underscore xi divided by the square root of S underscore xx times S underscore y. It measures the strength and direction of a linear relationship between x and y. R is always between -1 and +1. Positive R means as x increases, y tends to increase. Negative R means y tends to decrease. R equals 0 means no linear relationship, though a nonlinear relationship may still exist. In simple linear regression, R squared equals R squared. Y estimate sigma squared. Sigma squared measures the random variation around the true regression line. We need it for standard errors, confidence intervals, and hypothesis tests like t-tests and the f-test. The unbiased estimator is S squared equals SSE divided by n-2, where SSE is the sum of squared residuals. The denominator n-2 is the degrees of freedom, because we estimate two parameters, beta underscore 0 and beta underscore 1. This S squared is called the mean squared error, i.e. estimate sigma squared. Sigma squared measures the random variation around the true regression line. We need it for standard errors, confidence intervals, and hypothesis tests like tests, and the f-test. The unbiased estimator is S squared equals SSE divided by n-2, where SSE is the sum of squared residuals. The denominator n-2 is the degrees of freedom, because we estimate two parameters, beta underscore 0 and beta underscore 1. This S squared is called the mean squared error, or MSE, or MS. Y estimate sigma squared. Sigma squared measures the random variation around the true regression line. We need it for standard errors, confidence intervals, and hypothesis tests like t-tests and the f-test. The unbiased estimator is S squared equals SSE divided by n-2, where SSE is the sum of squared residuals. The denominator n-2 is the degrees of freedom, because we estimate two parameters, beta underscore 0 and beta underscore 1. This S squared is called the mean squared error, i.e. estimate sigma squared. Sigma squared measures the random variation around the true regression line. We need it for standard errors, confidence intervals, and hypothesis tests like tests, and the f-test. The unbiased estimator is S squared equals SSE divided by n-2, where SSE is the sum of squared residuals. The denominator n-2 is the degrees of freedom, because we estimate two parameters, beta underscore 0 and beta underscore 1. This S squared is called the mean squared error, or MSE, or MS. 11.5 Inferences concerning the regression coefficients. Once we've estimated the regression coefficients and the error variance, the next natural step is to make inferences about them. We want to answer questions like, is the slope significantly different from 0? What is a confidence interval for the intercept? In this section, we'll learn how to conduct hypotheses and construct confidence intervals for beta underscore 0 and beta underscore 1 using the t-distribution. Sampling distribution of B1. The sampling distribution of the slope estimate B is normal with mean equal to the true slope beta, and variance equal to sigma divided by S underscore xx. Since sigma is unknown, we estimate it using S, which is SSE over n-2. The standard error of B is then S divided by the square root of S underscore xx. This standard error is used for confidence intervals and hypothesis tests about the slope. Confidence interval for beta. A 100 times 1 minus alpha % confidence interval for the true slope beta underscore 1 is given by B plus or minus t underscore alpha 2 times the standard error of B. The standard error is S divided by the square root of S underscore xx. The critical value t underscore alpha 2 comes from the distribution with n-2 degrees of freedom. This interval gives a range of plausible values for the slope, capturing the true beta with 95% or 90% confidence, depending on alpha. Let's work through an example. We have pollution data with sample size n equals 33, so degrees of freedom is 31. From earlier calculations, S underscore xx is 4152.18, S underscore xi is 3752.09, and B is 0.9036. First, we compute the mean squared error. S squared equals S underscore y minus B times S underscore xi, divided by n-2. That gives 10.43. Taking the square root, S equals 3.2295. Using a t-table with 31 degrees of freedom, t underscore 0.0 to 5 is 0.045. The 95% confidence interval for beta is b plus or minus t times s over root s underscore xx. This simplifies to an interval from 0.8012 to 1.0061. We are 95% confident that the true slope lies between these values. Hypothesis testing on the slope. To test whether the slope is significantly different from 0, we use a t-test. The null hypothesis can be two-sided, beta underscore 1 equals 0, or one-sided, beta underscore 1 less than or equal to 0, or greater than or equal to 0. The test statistic is t equals b minus the hypothesized beta underscore 10 divided by the standard error, s over root s underscore xx. Degrees of freedom are n minus 2. The most common test is whether beta underscore 1 equals 0, meaning no linear relationship. In this example, we test whether the true slope beta is less than 1.0. From earlier, b equals 0.9036, s equals 3.2295. S underscore XX equals 4152.18, and sample size n is 33, so degrees of freedom is 31. S statistic t equals 0.9036 minus 1.0, divided by s over root s underscore XX, which gives negative 1.92. The p-value is the probability that a t-distribution with 31 degrees of freedom is less than negative 1.92. Approximately 0.03. Since the p-value is less than 0.05, we reject the null hypothesis and conclude that beta is less than 1.0. The negative t-value indicates the sample slope is below 1, providing moderate evidence for the one-sided alternative. In this example, we test whether the true slope beta is less than 1.0. From earlier, b equals 0.9036, s equals 3.2295. S underscore XX equals 4152.18, and sample size n is 33, so degrees of freedom is 31. S statistic t equals 0.9036 minus 1.0, divided by s over root s underscore XX, which gives negative 1.92. The p-value is the probability that a t-distribution with 31 degrees of freedom is less than negative 1.92. Approximately 0.03. Since the p-value is less than 0.05, we reject the null hypothesis and conclude that beta is less than 1.0. The negative t-value indicates the sample slope is below 1, providing moderate evidence for the one-sided alternative. Coefficient of determination, or slide, narration, or the coefficient of determination, measures the proportion of variability in the response variable y that is explained by the regression model. It ranges from 0 to 1, and is often expressed as a percentage. A higher R means the model fits the data better. 11.8 Analysis of variance, ANOVA. We now introduce analysis of variance, or ANOVA, in the context of simple linear regression. So far, we have tested the slope beta using a t-test. ANOVA provides an equivalent method, but it is based on partitioning the total variation into explained and unexplained components. Is this useful? Because while the t-test works only for a single predictor, ANOVA extends naturally to multiple regression with several predictors. In SLR, the f-test from ANOVA gives exactly the same conclusion as the two-sided t-test for beta, but the real power of ANOVA becomes clear when we have multiple x variables, where we need to test whether any of the predictors are significant. ANOVA in simple linear regression. We've already tested the slope beta using a t-test. ANOVA provides an equivalent method by splitting the total variation into explained and unexplained components. This approach is especially powerful because it extends naturally to multiple regression with several predictors. Why use ANOVA? Let's summarize why we use ANOVA. First, the t-test only works for one predictor. Second, ANOVA decomposes the total variation into meaningful parts, variation due to regression and variation due to error. Third, it produces an f-test that tests whether the regression explains a significant portion of the total variation. In SLR, this f-test is equivalent to the two-sided t-test for beta, but the real value of ANOVA is that it lays the foundation for multiple regression, where we need to test several slopes simultaneously. So think of ANOVA as a bridge from simple to more complex model. Why use ANOVA? Let's summarize why we use ANOVA. First, the t-test only works for one predictor. Second, ANOVA decomposes the total variation into meaningful parts, variation due to regression and variation due to error. Third, it produces an f-test that tests whether the regression explains a significant portion of the total variation. In SLR, this f-test is equivalent to the two-sided t-test for beta, but the real value of ANOVA is that it lays the foundation for multiple regression, where we need to test several slopes simultaneously. So think of ANOVA as a bridge from simple to more complex model. Partition of total variation, ANOVA. Here again we see the partition of total variation, SST equals SSR plus SSE. This is the same equation we saw earlier when discussing R. In the context of ANOVA, we emphasize that SST measures the total variability in Y around its mean. SSR measures the variability explained by the regression line. SSE measures the leftover unexplained variability. In SLR, the F-test based on this partition gives the same conclusion as the T-test for the slope, but when we move to multiple regression, this partition becomes even more powerful because we can test whether the set of predictors as a whole has any linear relationship with Y. Degrees of freedom, ANOVA. Degrees of freedom are crucial for constructing the F-test. Total degrees of freedom is N1, because we lose 1 degree of freedom when we estimate the overall mean of Y. Regression degrees of freedom is 1 for simple linear regression, since we have only one predictor. Error degrees of freedom is N2, because we have added to parameters, intercept and slope. And indeed, N1 equals 1 plus N2. This arithmetic consistency is a good way to check your understanding. Mean squares and the F statistic. Narration. From the sums of squares, we compute mean squares by dividing each sum of squares by its degrees of freedom. MSR equals SSR. 1 is the regression mean square. MSE equals SSE, and 2 is the error mean square, and it is our estimate of the error variance sigma. The statistic is then F equals MSR, MSE. Now think about what happens under the null hypothesis H, beta equals 0. If beta equals 0, then both MSR and MSE estimate the same sigma, so F should be approximately 1. If beta not equals 0, then MSR estimates sigma plus an extra positive term due to relationship, so F will be greater than 1. Therefore, large values of F provide evidence against the null hypothesis. We compare the calculated F to an F distribution with one numerator and n to denominator degrees of freedom. ANOVA table for simple linear regression. Most statistical software outputs an ANOVA table that looks like this. The table has rows for source, typically regression, error, or residual, and total. The columns are sum of squares, SS, degrees of freedom, DF, mean square, MIS, the F statistic, and the PU. For simple linear regression, the F-test is exactly equivalent to the two-sided T-test for the slope. In fact, you will see that T equals F. This is why you often see both T and F reported in regression output. They are mathematically the same for SLR. Relationship between T and F in SLR. This slide emphasizes the mathematical equivalence. T equals F. The T statistic we computed for testing H, beta equals 0, when squared, equals the F statistic from the ANOVA table. For example, if T equals to 0.5, then F equals 6.25. The p-value is identical for a two-sided T-test and the F-test. However, note that this relationship holds only for simple linear regression with one predictor. In multiple regression, the F-test tests all slopes simultaneously, while individual T-tests test each slope separately. They are not simply squares of each other. This example studies the effect of population size on ozone concentrations across U.S. cities. The data show ozone levels in ppb and population in millions for 10 cities. The task is to fit a linear regression model and test whether the slope beta equals 0 using the ANOVA approach. Part I. ANOVA F-test calculations. We begin with 10 cities. The sums are: sum x equals 13.7, sum y equals 1,282. The means are x equals 1.37 and y equals 128.2. Next, we compute the three sums of squares. S under xx is sum x squared minus sum x quantity squared over n, giving 19.261. S underscore xi is sum xi minus sum x times sum y over n, giving 31.86. And S underscore y is sum y squared minus sum y quantity squared over n, giving 77.6. These values will be used to build the ANOVA table. Step 3. Compute the regression coefficients. Slope b equals S underscore xi over S underscore xx, which is 31.86, divided by 19.261, giving 1.65 for 5. Intercept b equals y minus b times x, which is 128.2 minus 1.65 times 1.37, giving 125.933. So the fitted model is y hat equals 125.933 plus 1.65 for 5x. Step 4. Build the ANOVA table. SSR is S underscore xi squared over S underscore xx, which is 31.86 squared over 19.261, approximately 50 to 0.70. SSE is S underscore Y minus that same quantity. MS or is SS are divided by 1. MSE is SSE divided by N minus 2. And the F statistic is MS or over MSE. These will be used to test the overall significance. ANOVA table and decision. The ANOVA table shows regression sum of squares, 52.70 with 1 degree of freedom, giving mean square 52.70. Error sum of squares is 24.90 with 8 degrees of freedom, giving mean square 3.1125. The F statistic is 52.70 divided by 3.1125, which equals 16.93. The critical F value at alpha 0.05 with 1 and 8 degrees of freedom is 5.32. Since 16.93 exceeds 5.32, we reject the null hypothesis. Conclusion: there is a significant linear relationship between population size and ozone concentration, with a p-value approximately 0.003. 11.1 to testing the correlation coefficient, ρ. We now shift focus from regression to correlation. While regression focuses on the slope, the rate of change in y per unit change in x, correlation measures the strength and direction of the linear relationship between two variables. Both are mathematically linked, but they answer slightly different questions. Population correlation coefficient is denoted by the Greek letter ρ, and the sample correlation coefficient is denoted by r. Unlike the slope, correlation is unitless, and always lies between 1 and +1. A value near +1 indicates a strong positive linear relationship, near 1 a strong negative linear relationship, and near 0 no linear relationship. Correlation measures the strength and direction of a linear relationship between two variables. While regression focuses on the slope, the rate of change in y per unit change in x, correlation tells you how closely the data points follow a straight line. The two are mathematically linked, but they serve different purposes. Population and sample correlation coefficient. The formula for the sample correlation coefficient are as r equals xi, SXXCI. This is equivalent to the standardized covariance. It scales the covariance by the product of the standard deviations. A key result is that r equals are the coefficient of determination we saw earlier, so the square of the relation is exactly the proportion of variance, explained by the linear regression. This is a beautiful connection. The strength of the linear association directly tells you how much of the variation in y is explained by x. For example, if r equals 0.9, then 81% of the variation is explained. Testing the hypothesis ρ equals 0. No linear association. We often want to test whether the true population correlation ρ is 0, that is, whether there is no linear association between x and y. The test statistic is t equals r, and 2, 1 r. This t-test is exactly the same as the t-test for beta equals 0 simple linear regression. In fact, the two tests are mathematically equivalent. The beauty of this formula is that it allows us to test the correlation using only the sample correlation r, and the sample size n. We compare the calculated t to a t-distribution with n to degrees of freedom. Using the loblolly-pine data from example 11.10, we test whether there is no linear association between specific gravity and modulus of rupture. The sample size is 29, and the sample correlation coefficient r is 0.9435. The objective is to determine if the population correlation coefficient ρ is significantly different from 0, using a significance level of 0.05. Step 3. Compute the test statistic. Given r equals 0.9435 and n equals 29, so degrees of freedom is 27. The square root of 27 is about 5.1962. r squared is 0.8902, so 1 minus r squared is 0.1098, and its square is approximately 0.3314. Then t equals 0.9435 times 5.1962. divided by 0.3314, which gives 4.902, divided by 0.3314, resulting in t approximately equal 14.79. Step 4. Determine the critical values. For a two-tailed test with alpha 0.05 and 27 degrees of freedom, the t-table gives t underscore 0.025, approximately to 0.052. So the critical region is t less than negative to 0.052 or t greater than positive to 0.052. 5. Compare the computed t to the critical value. Our computed t is 14.79, which is much larger than 2.052, so it falls into the critical region. Step 6. Conclusion: because our computed t of 14.79 exceeds the critical value of 2.052, and the p-value is extremely small, we reject the null hypothesis that ρ equals 0. Final statement: there is overwhelming evidence of a positive linear association between specific gravity and modulus for loblolly pines. The sample correlation of 0.9435 is statistically significant at the 0.05 level, with a p-value less than 0.0001. Summary table for tests of ρ slide. This summary table shows hypothesis tests for the population correlation coefficient ρ. For all alternatives, two-sided, positive, or negative, the test statistic is t equals r times the square root of n minus 2, divided by the square root of 1 minus r squared. The critical depends on the alternative. Two-sided uses t beyond plus or minus t underscore alpha, 2 with n minus 2 degrees of freedom. One-sided upper uses t greater than t underscore alpha. One-sided lower uses t less than negative t underscore alpha. The assumptions: x and y should follow a bivariate normal distribution, or at least the relationship linear with normal conditional distributions and constant variance. Also, the sample must be random. In practice, this t-test is robust to moderate violations of bivariate normality, especially for larger sample sizes.